You know, I'm impressed each time I see the ship again, you know. It's so unique, and I think if you see it the first time, it's just very impressive to see this vessel with the rig, and you see there's something going on in that place with that many people who can live on that ship.
To be here on this boat myself for the first time, it's amazing because you really understand the magnitude of the science that is happening and has happened here. And as a scientist, it's really remarkable to be in such an environment and on a vessel that has been so significant to Earth science. It's a floating ocean lab.
I felt it the moment I stepped on board this ship for the first time 20 years ago, and I feel it today. That's my ship.
The Atlantic Ocean, just south of Newfoundland. For scientists, the Newfoundland ridges are where some of the Atlantic's most interesting ocean floor sediment drifts are to be found. And among them, the key to unlock the mysteries of past climate change.
We go back in history here and look at a time where we know the climate was extremely warm. And we found a place that the principal investigators of this expedition have, through many years of work, they have found this spot where we have an archive in the ocean sediments that we can read, and we can learn about the relationships between the oceans and the atmospheres, temperatures and chemistry. That is really the main topic.
On board the scientific drilling vessel JOIDES Resolution, affectionately called the JR by many, an international team of scientists is joining forces to recover sediments from the Paleogene period. This is a fascinating era in the geologic past when the Earth was a lot warmer than today, but somehow changed to something closer to our current, much cooler climate.
The Paleogene, this period of time that we're studying, that's from 66 to about 23 million years ago, looked very different than today. There were large tropical oceans and subtropical oceans, and polar oceans were much smaller. But as we progressed through this time period and we got closer to where we are today, those tropical oceans closed and polar oceans opened up, like the Southern Ocean, and here in the North Atlantic where we are, the oceans got wider and deeper. So the focusing and transport of heat on the planet by wind and by water was much different at the beginning and at the end of this Paleogene period. And so that's really interesting because it feeds back into these climate change events that we're studying, to trying to interpret and understand these climate events that we're uncovering in these ocean cores.
The mission? To understand how the Earth changed from this warm greenhouse world into a cooler one with large polar ice caps. The sediments of the Newfoundland ridges hopefully contain enough detail to determine precisely what happened, when, and why.
What we do is we go out and we make discoveries which give us a better understanding of how the world works. But those almost always build on some prior gain of knowledge from some other source. And so in our case, we're building very much on work that was recently done in the Pacific Ocean, where they reconstructed also sort of how the Pacific as an ocean basin worked. And here we are working in the North Atlantic, trying to understand, piece together in some respects how the global picture works.
By reconstructing our planet's climate history, scientists can gain insight into how the Earth's natural system reacts to changes in greenhouse gas concentrations. This is of major concern for society because mankind is releasing a lot of carbon dioxide to the atmosphere very quickly by burning fossil fuels. But the crucial question is, how much will global temperatures increase?
We know that we are releasing carbon dioxide into the atmosphere. We know that carbon dioxide is a powerful greenhouse gas. We can measure the amount of carbon dioxide in the atmosphere today, and we can measure the amount of carbon dioxide in the atmosphere in the past. So the trillion-dollar question is, what is climate sensitivity? What we mean by climate sensitivity is, for a given CO2 forcing, how much will global temperatures respond? And that is the trillion-dollar question that we are seeking to address with our expedition.
Climate history is recorded in little tiny critters that die and deposit their shells in the sediment. Unfortunately, on land, sediment is usually eroded. So if you have mountains rising up and there's sediment somewhere deposited, with time that sediment is washed down into the sea, and it's only in the sea that we actually find very well-preserved and continuous records of Earth history. And even in the sea, we have to be careful where we go, and we have to do a lot of surveys to find the best places where the sediment history books are extremely well preserved and have all the information that we need.
Now, when we're going into Newfoundland, we'll be going up into the Labrador current, written down along the side. Just for a reference with regards to the currents that we'd be working with as we were steaming to this site, you see my last position there at 0800, and we're just coming along towards our first location, and then operation starts.
So it begins.
First core, so the first shot into the seafloor comes up, and everyone's all excited. A lot of us got up early, even though we weren't on shift, because we just wanted to see the first piece of sediment. It's hard to describe that we're so excited about mud.
Look beautiful, that core. Now I'm ready to go to bed.
Looking at the first sample, Dick?
Yes, this is the core catcher.
We're looking for little tiny fossils about the size of well, the biggest ones would be about the size of a pinhead, and they're made of a mineral called calcium carbonate. These are our primary means of indicating how old the sediments are at this stage.
Extremely tiny forams.
No, it's barren, completely barren.
Actually, I can find only diatoms.
If you take the JR, the boat itself, and you add to it all the scientists and the technicians that are on board, you can think of the JR as a true time machine. As you drill down into the ocean bottom, you're drilling back in time. And you bring these cores up onto deck, and you have no idea what time period they came from, but it's the people on board the JR that tell us that story. So we have two teams of people that are basically what I call the keepers of time. So these are the people who actually can figure out where we are in time.
We hope that there are some foraminiferæ in there that tell us the age of the sediment, so that we can get a good handle of what we really get in our course.
The biostratigrapher is basically a biologist who just looks at biology in past oceans. They not only know all the organisms of their group floating about in the open ocean today, they know that for every single time period for the last 150 million years. It's unbelievable. So that gives us a first guess of where we are in time. And the second team, the paleomagnetists, they actually look at which way the North Pole is pointing. And so if you look back in time, the North Pole is flip-flopped, which is kind of incredible, but the magnetic polarity of the Earth itself has changed. And they look at those stripes, and together, the paleomagnetists and the biostratigraphers are keepers of time. So they put us in a single place in time. And when you figure out where you are in time, you actually want to go out and see what was going on in the world. And so that's my job. If you come into the core lab and we're opening one of these cores where we think is around one of these really interesting time period where the world is changing, sometimes you open it up and you miss it. But other times you open it up and you see the world change before your very eyes. And that's super exciting.
The first drill site revealed a series of dramatic turning points in life and evolution on our planet. However, the scientists can't always be immediately sure if they have recovered sediments from the targeted events.
The reason for the excitement is that we've hit some really juicy targets. First hole, first site, 3 major stratigraphic events that everyone's excited about.
We're looking at the KT boundary. This is the geological boundary between the Cretaceous and the Paleogene, the boundary where the dinosaurs went extinct, but a bunch of other things happened. There was a meteorite impact. It looks like we have captured in this core the ejecta from that impact event.
Dinosaurs? No dinosaurs. Dinosaurs? No dinosaurs.
So pretty exciting.
Ocean drilling always comes with challenges. Sometimes, heavy weather or strong currents can play havoc with operations, and drilling tools and equipment will need tweaking to work properly. When drilling thousands of meters below the sea surface and hundreds of meters into the sea floor, things can get complicated very quickly.
What had happened is that we were trying to recover a complete record of the Eocene-Oligocene transition, where the Earth goes from being this really warm greenhouse into being a glaciated ice house. And it looked like there was this gap, basically, where the transition occurred in the interval between two cores from the first hole.
Think of what the scientists do as reassembling the pages of a long-lost history book. It only makes sense if they have all of the pages and in the right order. But sometimes it's hard to tell if every page is accounted for. In this case, there was some serious doubt as to whether the team had succeeded in bringing up a vital core covering an important geologic interval.
Now, the other possibility is it's one of these.
No, that's
No, the question would be if it's in...
Well, it could be like in here.
So we're looking for the signal of Antarctic glaciation, maybe glaciation in the northern hemisphere, by looking for flickers in calcium carbonate preserved on the seafloor in the North Atlantic.
And that basically reflects variations in the acidity of the ocean and how much carbonate the ocean can store. The other thing that's important here is that we could spend a whole day, basically about $100,000, to go and make sure that we have a complete record. But we may actually already have it on the table in front of us.
So that's what the excitement's about.
It was very exciting because it showed how everyone's input was really important to determine whether, in fact, that core had done what we wanted it to in the first place. And in the end, of course, we decided that it had, and that it wouldn't be necessary to go down and get a sea hole after all.
This is what has been described as the mother of all climatic shifts in the last 65 million years of life on this planet.
Earth becomes glaciated for the first time, right here.
Please confirm this on camera, Paul. What do you have?
I think we're in the Eocene down. And what's really nice is that we've got lots of carbonate in this sample. And that's really unusual for the Eocene-Oligocene boundary interval.
I feel like we just scored a big prize.
Well, we just got the Eocene-Oligocene boundary, which we weren't sure we were going to get, so we're all pretty excited about it. And when it came in, then we cut off the end of that core, and it gave us that heart shape, or a smile. It was like, the Eocene loves you.
So that's this period of time when these ice sheets first get triggered down on Antarctica. And one of the neat things about being here in the North Atlantic is that we can perhaps assess what was going on at high latitude in the north at the same time. That's been a difficult thing to assess until this expedition.
Awesome! It's coral from an ancient atoll. Can you see?
This was a really crazy day. Just as I got off shift last night, we were in the Middle Eocene, and then we went into the Lower Eocene, that white ice cream looking stuff. We jumped across the Paleogene-Eocene boundary. This is the Paleogene, maybe the PETM, probably not. Then we went through the Paleogene, jumped across the Paleogene into the Cretaceous, through the Cretaceous, and now we're at the Cenomanian-Turonian boundary, which is this amazing oceanic anoxic event, which we're all really excited about. That must be 40 million years we've gone through in 24 hours. Pretty amazing.
These are extreme events in the carbon cycle, often associated with warming and stagnation of the ocean, so that you end up with these accumulations of carbon. It's a brilliant way for the Earth's system to get rid of excess CO2 in the atmosphere by burying carbon as organic matter in the ocean floor.
These events that are anoxic events that preserve organic matter, and in some cases this organic matter can accumulate, and under the right conditions and right temperature and burial can be the source of oil and natural gas. This carbon was stored naturally by the Earth's system. So in a way, you know, what we've been doing the last couple hundred years is tapping into this natural storage and re-releasing it into the atmosphere. You know, that's why we're interested in studying these kinds of things, because it helps us understand sort of both natural sequestration processes and how we've sort of influenced that.
The Earth system will handle this CO2 that we're putting into the system. The question is whether our civilization will be able to handle it or not.
This is a core, or this is a site anyway, which will go down truly in history, I think. Because we have by far and away the most detailed record of this sort of transition into a fully glaciated world that exists anywhere on the globe, right here.
This is pretty cool. So, if you see right here, have this transition from dark clay to light clay. It doesn't look like much, but you know, ask Antarctica what's going on, and it'll be, you know, no ice and ice.
No ice on Antarctica, ice on Antarctica. You can just see it. There's nothing that quite comes close to either seeing something on the core table or plotting a data set for the first time and looking at it and realizing that you're the first person to have seen some fundamentally new insight into how the world works. What job could be better than that?
This is a marmalade core. It's our last core, which makes it bittersweet.
We did it, and amazingly, you know, we covered exactly 5,400 meters, more than 5 kilometers.
I have the very last section to the very last site.
Expedition? End of expedition.
This expedition was very successful. A Grand Slam home run in baseball terms. But there was a moment when it was not clear whether the team was on the right track. Some drilled intervals turned out to be younger, and others a lot older than the primary targets that they were looking for. So to retrieve exactly the right intervals, the team needed to change the plan underway.
What we essentially did is we went on a hunt for the right stratigraphic interval. It was the most interactive drill site finding exercise and expedition that I've ever seen, and it was extremely successful.
So one of the great aspects of science is being able to adjust, you know, and change your attitude, your views on how something works. Throw away the preconceptions that you started off with, and and take off on a different direction. That's really one of the great hallmarks of science. It's one of the great hallmarks of this particular drilling program, is that ability to react, to make sure that you maximize the return to everybody involved. Not only the scientists on the ship, not only the people, in the program on the beach, but also the broader public who are ultimately, hopefully, going to benefit from the kind of work that we do.
What's up? What's in front of us?
Land.
There's a sense of collective accomplishment.
Yep, we did it.
It's been fantastic.
That's great to see land after 2 months of working.
A lot was done. It was pretty cool to be a part of it.
It's one of the great pleasures in life to be part of a group of people who are all working towards the same objectives. And in this particular case, we had 30 scientists from all over the world, all sort of focused on this particular expedition, all thinking about what they're going to do with the material that we recovered. It is such a pleasure to be part of it because you know that everybody, right down to the cooks, right up to the captain, they're all aimed at the same basic objective of making sure that our science works the best it possibly can. And that's terrifically liberating.
Ocean drilling is just this remarkable feat of technology. I like to go out and just watch how they do it. So the JR has been instrumental in helping us understand how Earth and life has evolved for over 100 million years. And coming out here, being on the JR, allows me to ask the sort of questions to understand the sorts of futures that we'll be facing.